Now we are going to sample this sequence. We are going to sample the sequence, and the sampling frequency that is given to us is a frequency that is omega s equal to 12,000 pi. Okay. So maybe we should take a closer look at the values and then see what is the expression that we are getting, and so that we can appreciate what is going on with this particular example. Okay. So tell me, what is the highest frequency component here? The highest frequency component 2 pi. So omega is equal to 4,000 pi, that is equal to 2 pi f naught, this is omega naught. So f naught is equal to 2000 hertz, 2 kilohertz is the response. So Nyquist frequency, Nyquist rate Fs should be greater than or equal to 4 kilohertz. We are told that we are using a sampling rate of 6 kilohertz. Okay, so then correspondingly omega s will come out to be 12,000 pi. Okay, I hope you are able to see what is happening here. All right. So when you do this, what happens? You have xc of t, which is cosine 4,000 pi t. The discrete time signal is obtained by taking the continuous time signal and sampling it at a period Ts, and Ts is equal to 1 over 6,000. Okay, the sampling frequency is 6,000 hertz, so Ts will be 1 over 6,000 seconds. Okay, we use this as that. So what does that come out to be? Cosine 4,000 pi, you are going to replace T with NTS, N times Ts is divided by 6,000, Ts is 1 over 6,000. So this comes out to be cosine 2 pi by 3n. In terms of the discrete time frequency. So the discrete time frequency omega naught is equal to 2 pi by 3. Remember, the discrete time frequencies are periodic with period 2 pi. So anything between 0 and 2 pi is, you can treat it as the sort of the fundamental frequency, and then you can look at it in terms of the higher frequency components. So this is how you would do the sampling process, and this will be from cosine 4,000 pi t. Through the process of sampling, you will produce a discrete time signal which is cosine 2 pi by 3n, and then you can look at it, the behavior of this signal. Now I also want you to take this opportunity to study the sampling process. That is very important. So in the sampling process, you started out with two delta functions, one at 4,000 pi and another one at minus 4,000 pi. What other frequencies got generated in the sampling process? Okay, in the sampling process. Okay, the sampling process, if you were to look at it, is the sampling process. Remember, we said you are multiplying the continuous time signal with the Dirac delta signal. So first step is you are going to say, okay, what is xc of j omega? That is the continuous time signal. The continuous time signal is pi times delta of omega minus 4,000 pi, delta of omega minus 4,000 pi. Okay, let me get omega minus 4,000 pi plus delta of omega plus 4,000 pi. Okay, so that is xc. Now, what is the s of j omega, the Dirac delta, s of j omega, that is 2 pi divided by Ts summation k equal to minus infinity to infinity delta of omega minus omega s times k. Okay, so basically, so you have two Dirac deltas which is part of your input, and you have these Dirac deltas which are spaced at omega s, and you are going to convolve these two. Okay, remember that this is, so the s of j omega is equal to 1 by 2 pi xc of j omega convolved with s of j omega. Okay. So, make sure you take care of the scale factors. This will come out to be pi over Ts. The overall scale factor is pi over Ts. Okay. Now, these delta functions now are going to get replicated. So, basically wherever. So, what you will get is an infinite sum k equal to minus infinity to infinity delta of omega minus 4000 pi minus omega s times k. Okay, so that means wherever the Dirac delta is located, these delta functions which are part of your input spectrum, they will get shifted to those values. And the other delta function will be delta of omega plus 4000 pi minus omega s into k. Okay. So, two things to note. One is you will get a scale factor of pi over Ts. And now you will get Dirac deltas. If you take k equal to 0, where will you get it? You will get it at plus 4000 pi and minus 4000 pi. That is the input signal. Now, when you take k equal to 1, these two delta functions will now be shifted over to the sampling frequency, which is 12,000 pi. K equal to minus 1, they will be shifted to on the other side. So, let us write it down numerically, and then you will be able to appreciate it in a very simple manner. Okay. So, what we are looking at is a sampling frequency which is 12,000 pi. We have the deltas sitting at omega minus 4000 pi minus k omega s, and another delta sitting at omega plus 4000 pi minus k omega s. Okay. Now, if I take k equal to 0, then I will get a delta function at 4000 pi from this contribution. This will be a delta function at minus 4000 pi. Okay. Take k equal to 1. K equal to 1, this Dirac delta function will be shifted by 12,000 pi. So, this will go to 16,000 pi. How did you get 16,000 pi? 4,000 pi plus omega s. This is minus 4,000 pi plus 12,000. This shifts to 8,000 pi. K equal to 2. It will shift by 24,000. So, then this becomes 24 plus 4, 28,000 pi, and this becomes 24,000 minus 4,000, this becomes 20,000 pi. Okay. And let us take one last example, k equal to minus 1, then what happens? This goes to minus 8,000 pi, this goes to minus 16,000 pi. Okay. So, you can see how these, so let us say that we will color code k equal to 1, we will color code with pink, okay. K equal to 2, we will color code with blue, and k equal to -1, we will color code with this one. Okay. So let us look at how the spectrum looks like. K equal to 0 was green. Okay. K equal to 0 was green. So let us color code minus 4000 pi and 4000 pi. Scale factor is pi over t. K equal to 1 was pink. K equal to 1 is centered around 12,000. On the plus side, it will go to 16,000 and this will become 8,000. And then go one more time, we said k equal to 2. What happened? I thought we changed the color to blue. Okay. We will make it blue. Okay. So, which means that now we will now have to extend our axis, extend this axis to 24,000. 24,000 plus 4 will be at 28,000 pi, 28,000 pi, and this will be at 20,000. 20,000 pi. Okay, so basically you can see the that copy coming, and of course the last one will be brown. We will scale this one with the brown. Okay, so in the process of sampling, the original spectrum scaled by pi over t, the two Dirac delta functions, and then centered around omega s, 2 omega s and so on, minus omega s, all multiples. So this corresponds to, green corresponds to k equal to 0, pink corresponds to k equal to 1, the blue corresponds to k equal to 2, and the brown corresponds to k equal to -1. Okay. So you can see how an infinite number of copies have been generated through the process of sampling. You started out with 4000 pi and minus 4000 pi, but in the process of sampling you have generated other copies of the signal. Now, if you want to do reconstruction, what will you do? You will go from omega s by 2, so basically your filter, ideal reconstruction filter, will go from minus omega s by 2 to omega s by 2. Okay, what is omega s by 2? Is omega s is 12,000. So this will be from 6,000 pi to minus 6,000 pi, and the sampling free and the scale factor will be equal to Ts. So look at this dashed line. This is the reconstruction filter going from minus 6,000 pi to 6,000 pi. What will it do? It will remove all the unwanted copies of the signal. It will scale your signal back to the correct value, and what you will then be left with is two delta functions, one at minus 4,000 pi and 4,000 pi. If you combine them, you will get back the original signal. Okay. And I hope that this particular example sort of ties it all together, where you are looking at a practical situation where you going from continuous time to discrete time, that was straightforward. But what else happened in the process of conversion, that is good for us to know. What all copies did you generate? This sheet will tell you what all copies you generated, corresponding to k equal to 1, k equal to 2, and all positive and negative values of k. And then finally, what happens when you want to do the reconstruction process? What will it do? It will remove the unwanted copies and retain the original signal, so you can reconstruct the signal back. So with this, we will stop for today's coverage. What we will cover in the next class is just a quick introduction to the last step. So we went from continuous time to discrete time, that is a C to D converter. But the next step will be to quantize the signal. So quantize it from infinite precision to, let us say, some number of bits, 12 bits or 16 bits. What is that process of quantization, and how do we understand quantization? So with that, we will complete an introductory coverage of the process of sampling and reconstruction. Of course, there are more details that we will be studying after we have studied the discrete time Fourier transform. We will come back to looking at the process of sampling and reconstruction, because it will give us some new insights once we have a good understanding of the discrete time Fourier transform. So we will stop here and pick it up in the next class, where we will talk about the aspects of quantization. Thank you.